Assalamualaikum and good morning, Dr. Muhammad Razi, Dr. Wan Aizon, and everyone. We are Group 2, and our project is titled Internal Flow Verification and Parametric Analysis of NASA 0012 Blade Prestige using CFD. The purpose of this presentation is to explain how we design a simple NASA-based blade profile, build a CFD workflow, validate the pressure and trend against a published NASA 0012 study, and then use the model to analyze inlet velocity and incident effects in a blade passage. Our group members are Muhammad Shamil bin Ismail, is me, Muhammad Nufahmi bin Jaafar, and Song Jun Chen. In this presentation, we will focus not only on the numerical values, but also on the flow behavior, pressure loading, streamlines, wake development, wall response, and loss trend. This follow the project requirement that the emphasis should be on engineering interpretation rather than exact numerical matching. This slide shows the structure of our 15-minute recorded presentation. The project brief require us to include design rationale, CFD methodology, validation, finding, parametric trend, and key engineering insight. So our talk follows that order. First, I will introduce why NASA 0012 was selected and how the geometry and operating metric were defined. Then Fahmi will explain the CFD setup, mesh strategy, mesh sensitivity, and the base case flow field. Finally, Song will present the validation result, the velocity and incident parametric studies, and the engineering interpretation. The main idea is to show a complete workflow. We begin with a control blade design, check the CFD method using a published benchmark, and then apply the same workflow to the periodic blade passage case. This makes the latter trend easier to justify because the method has already been checked against literature. We selected NASA 0012 because it is a simple and well-documented aerofoil profile. The first two digits indicated zero chamber, and the final two digits indicate a maximum thickness of 12% of the cord. This symmetry is important because it reduces geometry bias. In other words, when the flow behavior changes, the change is mainly caused by the operating condition, such as angle of attack or incident, rather than by an asymmetric blade shape. Another reason is that NASA 0012 has many available experimental and numerical studies, especially pressure coefficient data. This makes it suitable for validation. For this project, we use it as a control blade section so that we could focus on pressure distribution, velocity field, boundary layer behavior, wake formation, and loss trend. The profile therefore fits the project objective to study turbomachinery flow physics using a NASA-based blade. Our study used two related computational domains. The first is the literature validation domain. It is an isolated NASA 0012 aerofoil case, and its purpose is to compare the computer pressure coefficient distribution with the published data from Ruck et al. This step helps us check whether the CFD workflow can reproduce the main pressure trend around the aerofoil. The second domain is the periodic cascade flow domain. This is the main internal blade passage model for the group project. The upper and the lower boundaries are periodic, so the single passage represents a repeated blade row. This separation is intentional. The validation domains give credibility to the pressure prediction method, while the cascade domain is used for the required turbomachinery internal flow and parametric analysis. Therefore, validation and application are connected, but they are not treated as the same geometry. This slide summarizes the blade passage geometry and the operating metric. The cascade model used the same NASA 0012 profile with a chord length of 0.15 meter and a pitch of 0.15 meter. Therefore, the solidity is 1.0. The stagger angle is 30 degrees, which gives a clear periodic blade passage arrangement for the internal flow analysis. The base case is CV20 and 100, which use an inlet velocity of 20 meter per second and zero incident. From this base case, we performed two control parameter studies. In the velocity study, the inlet velocity was varied to 10, 20, and 30 meters per second, while incident was kept constant. In this incident study, the velocity was fit at 20 meters per second, while incident was changed to 0, 5, and 10 degrees. This metric allows one inlet variable to be isolated in each study block. That's all from me, and then we will continue with Fahmi.
Hi all, my name is Fahmi. My ID number is P154036. And now I will explain regarding the CFD setup. The same general solver strategy was used to link the validation and cascade simulation. Hence, the simulation will perform as a steady pressure-based CFD calculation, and the A is working as a working fluid. And the turbulence model was SSTK omega. The SSTK omega turbulence model is a two-equation model. Combines the near wall accuracy of the model and then a robustness of the model in the free stream region. And by blending both formulation, it provides an improved prediction of boundary layer behavior, flow separation, and pressure gradient, and making it suitable for a wide range of reasoning flow estimation. And then this model was selected because it's commonly used in a near wall aerodynamic flow. It is very suitable to advise pressure gradient behavior and blades, and for the validation model. And for the benchmark, the inlet velocity was 20 meter per second. And the airflow angle of attack follow the benchmark case as a benchmark measurement. And then for the cascade model, the inlet velocity of the inlet angle will change according to the parameter matrix. And then the outlet was treated as a pressure outlet. And the blade surface used a non-slip wall condition. And for the cascade passage, the periodic boundaries represent the repeated blade-to-blade flow. And the main outputs were the pressure coefficients, velocity contours, pressure contours, streamlines, and weight profiles. So this is the mesh strategy. We focus on the regions where the flow change more strongly. So near the leading edge, and then we refine the mesh to capture the strong pressure gradient along the local acceleration near the blade wall. And then where we near the blade wall, we capture the boundary layer refinement was used because the wall shear and near wall behavior are important for interpreting the possibilities of separation. So the trailing edge makes the region also refined, since the weight profile in the one of the main of the source of aerodynamic losses in the blade passage. So we check the wall Y plus value to make sure that near wall treatment was suitable for the model. So this slide show the representative of validation and cascade mesh figures. So together with the neo Y plus evidence. So this purpose of this mesh design was not only to obtain the converged solution, but to ensure that the pressure and weight profile and surface co-interpretation have enough resolution to capture the data. So for mesh sensitivity, we do not rely on a single grid. So the final decision was based on the combined evidence from force coefficient, pressure coefficient distribution, near wall quality. In the validation model, that the fine and extra fine mesh will compare. So the lift coefficient difference was about 1.34%, and the drag coefficient difference was about 1.57%. So the pressure coefficients root mean square error was 0.00787 pressure coefficient per unit. So this means that the flow field predicted was sufficient and stable for the trend analysis. So even though the small sensitivity remained in the lift coefficient, the most important point is that the pressure distribution and overall aerodynamic pattern did not change significantly where further refinement. And therefore, the selected mesh was considered adequate for this setup simulation, especially because of the project objective is to interpret the flow trends and physical behavior rather than to obtain the exit force value. And then this slide presents the base case or benchmark case flow field, which is refers to the case of the later parametric operation. This benchmark case used an inner velocity of 20 meters per second with zero incidence. And then the velocity of contour show the local acceleration as the flow moves throughout the blade passage, especially the near blade surface and around the narrow passage region. The pressure fields show that the expected pressure difference across the blade surface, which is related to blade loading. The streamline patterns helps confirm that passage flow is continuous. And then the downstream weight forms behind the trailing edge. We read this plot together because one of the controller can be misleading. So velocity pressure and streamline together show that how the blade turns and accelerates flow, and they provide the baseline for the judging with the velocity incidence change in the next slides.
Next, I will present the validation and analysis part. The validation reference was the AA0012 studied by Rick. The main calculation variable was the surface pressure coefficient, CP. The validation cases used inline velocity of 20 meters per second. number of approximately 119,000 and angles of attack of 2, 4, 6, and 8 degrees. In this project, the aim was not to match every experimental data point exactly. Instead, the aim was to check whether the CFD result captured the mine pressure gradient trend around the airflow. This is consistent with the project requirement, which emphasizes flow structure, pressure trend, and velocity pattern comparison. After this validation step, the same CFD workflow was used to support the cascade parametric study. This slide shows the CP comparison between the assay's result and the digitized data from the rake. Overall, the CFD result captures the main pressure distribution and trend as angle of attack increases. The pressure difference between the upper and lower surface becomes stronger, and the suction side pressure becomes more negative near the leading edge region. The pressure side agreement is generally closer than the suction side agreements at a higher angles of attack, especially near the leading edge suction peak. The CFD curve shows a larger deviation. This is reasonable because our simulation uses a steady two-dimensional INS model. We also published the data include experimental effect and a different numerical approach. But therefore, the validation conclusion is not that every value is exactly matched. The correct conclusion is that the CFD workflow reproduces the mine aerodynamic pressure trend, and it is suitable for comparative flow behavior analysis in the cascade study. The first parametric study is the inlet velocity study. Here, the incidence is kept constant, and only the inlet velocity changes from the 10 to 12 and 30 meters per second. The velocity contours shows that the absolute velocity level increases with the inlet speed, which is expected. However, the normalized comparison is more useful for understanding the flow pattern because it separates the effect of the speed magnitude from the signal of the flow field. The wake and loss result shows that the normalized pressure loss coefficient decreases from about 0.0243 to about 0.189 as velocity increases. This indicates that within the tested range, higher inlet velocity reduces the relative viscous loss contribution with the geometry and incidence remain fixed. The key point is that the inlet velocity changes the intensity of the flow and the loss response, because it does not completely change the passive flow topology. The second parametric study is the incidence angle study. In these cases, the inlet velocity is fixed at 20 meters per second, where the incidence changes from the 0 to 5 and 20 degrees. Compared with the velocity variation, incidence has a stronger effect on the direction of the flow entering the blade passage. The distances, the leading edge alignments, and modifies the pressure in loading. The velocity and the streamline fingers show that the flow path and the downstream wake are displaced as incidence increases. The wake profile at x over c equal to the 1.2 shows that the 10-degree cases has a stronger wake defeat than the lower incidence cases. The pressure loss trend also changes with the incidence. The 5-degree case gives the lowest loss among the 3 tested cases, while the 10-degree case increases loss again. This suggests that the geometric zero incidence condition is not necessarily the minimum loss condition for this simplified passage. This slide connects the numerical result to the flow physics. First, the streamline impedance shows passage acceleration and wake flow motion downstream of the trailing edge. Second, the wall friction result gives the information about how the near wall flow responses to the pressure gradient and incidence change. Third, the separation assessment combines all skin friction behavior, reverse flow events, and streamline topology. Under the tested conditions, nuclear sustained separation or recycle circulation zones was detected. This does not mean there is no loss. Loss can still be generated by boundary lower growth. wall shear and wake mixing. The main engineering insight is that the incidence changes the alignment between the incoming flow and the blades. So it affects the boundary layer development and wake more directed than the velocity magnitude law. Therefore, inline angle control is important in blade passage operation. To conclude, this project successfully combined blade design, safety validation, and the parametric flow analysis. The AAC0012 profile was suitable because it provided a simple and controlled blade geometry and with the available reference data. The mesh and near wall checks spotted the safety interpretation and the validation against the record shows that the main pressure coefficient trend were captured. In the cascade study, changing in light velocity mainly affects the intensity of the flow and the normalized loss response. Changing incidence had stronger effect on leading edge alignment, weak development, and pressure loss behavior. No sustained separation or recirculation region was detected under the combined criteria, but weak and wall effects still contributed to loss. Overall, the study shows that validated safety workflow can support the preliminary mechanically blade passage assessment and the engineering judgment beyond the numerical matching. Thank you.